Hello everyone, welcome to another video. In this video I want to discuss with you about one of the topics that we normally address a lot in software engineering, which is coupling. Uh, Probably you've all heard about what coupling is, but just as a simple explanation, coupling is the degree on which things depend on each other. Okay, the higher the coupling means that the higher this degree of dependency, which means that if you change something on one of them, the other one is most likely to break. Okay, whereas if you have lower coupling, means that this dependency relationship between two components is not very big, and therefore uh, the likelihood of a change in one component breaking another is much less. Okay, it's less likely. Okay, and there's this rule that we tend to go on software engineering, which is let me decrease here the font size, which is low coupling, high cohesion. Cohesion. Think I'm spelling it correctly. If I'm not, please forgive me. And so with low coupling and high cohesion, what we want to achieve, generally speaking, in software engineering is that two components or components in general, they should not have this relationship between one another of dependency. They should be as independent as possible from one another. Okay, hence low coupling. But high cohesion means that things, generally speaking, things that belong together, they move together. Okay, I think of this as an example. In the real world, if you're in the kitchen, high cohesion would mean that you would sort all let's say all the knives are together and all the forks are together, all the spoons are together. Okay, they are of the same kind, so they are together. Okay, so translating this to software engineering, you probably get the point that I'm making. Okay, for example, if you're developing a feature for managing a customer, probably those the things that you develop that relate to managing a customer, they should all be on the same place. Let's say on the same folder or something like this. So generally speaking, this is the concept of cohesion. But my point today is not about cohesion; it's about coupling. Most importantly, because we tend to think that coupling is inherently bad. Okay, but if you think about it, in our real world scenario, uh, coupling is sometimes positive. Okay, it's something that we should fight to the best of our abilities, but it's something that we might have to live with because that's just how things showcase in the world, or in this case in our software. um, so coupling is something that will always exist, and is something that we don't the thing that we have to do is to learn how to live with it, and how can we make use of it, knowing that it's inevitable to have some kind of coupling. Okay, so as you develop software, and as software gets more and more complex, it's really hard to move away from coupling. Okay, so the idea is to always have a certain degree of coupling, which we will always have, but take the most benefit out of that when comparing to whatever downsides we know that coupling has. Okay, so we should try to take as much advantage as we can from coupling. Okay, But there are a lot of types of coupling. Okay, I actually have this message here, this screenshot I took from a YouTube video, which I will link in the description, where this video explores in much more detail that I will do here, the concept of coupling and the different types of coupling. Okay, which I actually find really interesting. All of this almost catalog of coupling, because when we are developing our software, we're just thinking about coupling between small components, like having concrete instantiations of a class and not using, for example, an interface at this low level to decouple those two low-level implementations. Or, for example, if you're talking about architecture and you have two systems, two components, in this case a component is a system, two systems that communicate via REST API, you know that inherently that there's some kind of coupling there. Okay, and how can you move away from that? Well, you always have the case of using queues, but you're still coupled. Even though you're not coupled with a system, but you're coupled with a broker in this case. But there's still a small coupling, but on a different level. And some examples that you will see on this video are really interesting, like protocols. Like we on our software, for example, if we send emails, we normally use behind the scenes SMTP protocol. So we are coupled to a specific protocol. In this case, the coupling is less risky because the SMTP protocol is something that is stable. So we shouldn't expect a lot of instability coming from that protocol. Okay, but you still have some kind of coupling. That's what I mean. I highly recommend watching the video that I will put down below on the description. But yeah, for now, just have in mind that we can have we don't only have coupling at the code level. There's multiple couplings on multiple dimensions. Okay, but I want to explore, and the reason why I'm making this video is because I want to explore this kind of coupling in a more generic way, and I want to bring you in a concept of fan-in and fan-out coupling, let's say. Okay, so let's do some drawings here in a more generic term. This whatever boxes I will draw here, they can be like code classes, or in a high level systems, as an example microservices. So they can be, depending on which level you're talking about, they can be and mean different things. So let's, for simplicity's sake, let's think that this is microservices. Okay, just because if we think systems, probably it will be easier. Okay, let's say that we are building some kind of architecture and we have here microservice, I don't know, Z, we have microservice, I don't know, X, and we have microservice W, something like this. Okay, and we have here somewhere here a microservice Y that all of them depend on something like this. Let's say something like this. Okay, so just by looking at this, you can easily think that, okay, this component here, this service here has to be highly available, because if and I'm assuming that, of course, this is like synchronous communication, or that you need this service to be up and running. But anyway, so you immediately look at this diagram and you say, okay, this arrow, all of the arrows are pointing to this service. If this service is down, the propagation will happen backwards. So all of these services will be somehow impacted. Okay. So you have here the coupling between these services and this service on this direction. So this is like coupling direction. Okay. But the other way around is not true. So if any of these services goes down, this service is still up and running. So there's no coupling from Y to here. Okay, so there's no coupling. Okay, no coupling. Okay. And the reason why I'm showing you this is because based on this coupling, you can infer stability of components. Okay. So, as I said before, the reason why I'm making this video is to discuss fan-in and fan-out coupling. So in this case, CFI, fan-out, no, CFO, it's like a component, let's say component fan-out CFO. And then component fan-in, say CFI as an example. Okay. So the fan-out is when a component points to another component. Okay. So in this case, Z points to Y. So the fan-out is 1. But CFI here is 1 because here is 0 because no one is pointing to Z, and this is the same for this one here. Okay, same one for this one. Okay, but in the case of Y doesn't point to anyone else, so it doesn't depend on anyone. So the fan-out is 0, but the fan-in is 3. Okay, because this component has 3 other components that depend on it. Okay, and just by looking at this, you can infer something really simple, that a component that has no dependencies, so a component that points to no other components, tends to be more stable. So more stable on this side of the spectrum. But a component or components that have a lot of fan-out, meaning a lot of dependencies, they tend to be less stable. Okay. And so this is something that when you're designing components, be it on a code level or be it at the at an architecture level, something that you should be thinking about. And the reason why you should be thinking about is because based on this stability, you can assign specific resources in people to work on such components. Okay, let's say that this component is like in this case, let's say it's an e-commerce application, and this component is the payments, and this is like really critical. It cannot be down for any reason. So if you have an intern on your team or a lot of junior people, you would not put them as responsible people for this component. Why? Because a chance or an error on this component can have a lot of effects, let's say downstream. Okay, so downstream as in services that consume or services or components that consume this one. So you probably put your more senior people on this component that has that is more stable, okay, because that a change here would have a lot of impacts downstream. Okay, there's actually a formula that is used to compute the stability or instability of something, which is this. So let's say stability equals fan out divided by fan out plus fan in. Okay, so this is the formula for stability. So let's say in the case of y, let's say stability of y equals how many is it pointing to? It's pointing to 0 divided by whatever here, doesn't matter. I mean, it actually matters, but it would be 0 plus 3, and this is 0. So stability of y is 0, and the 0 of stability means that is a lot of really stable. So really stable. Okay, by contrast, for example, z, let's do this, stability of z is how many it has as a fan out, which in this case is 1, then fan out, fan in, and that will be 1. And as you can imagine, 1 means that is really unstable. Okay, and so the range is normally between 0 and 1. Okay, so a component, of course, if a component is really isolated, then it's like this is 0 by 0, so it's, but normally as a part of an ecosystem, components, they depend on something. Okay, be it on the code level, components on the code level or system level, but this stability range goes from 0, which is really stable, to 1, which is really unstable, which in this case, as you can see, z is something that is really unstable because it has only dependencies. Nothing depends on it. It depends on a lot of things outside of it. Okay, there's something that I would like to go about, which is there are a couple of I don't want to call it laws, but I think we generally call them laws. But there's a law called postal law, which pretty much means that you should be conservative on what you do, but liberal on what you accept. And this, of course, is not political, but rather let's say system-wide. I don't remember exactly on which context this law just showed up, but again, to repeat, postal law just says that you should be conservative on what you do and liberal on what you accept, which in this case of a system, let's say Y was really, really strict as far as API, contracts, and so on. So any minor change on the contract would mean that everyone else downstream will have to be really, really obedient. And that sometimes might be the effect we want. But if that's the case, then if we are really, really strict on contracts and whatever we accept as an input, means that we are more likely to break things on the downstream. But if you're more liberal on the contracts, let's say, for example, you have a date time. You have a field that is a date, okay? And you accept this date both as a string or as a, I don't know, ISO date format. So this means that this guys here, if they send you a date in the ISO format or as a string in other format, you still accept and consider the data as valid. Okay. So this is being more liberal on what you accept, which means that if you're more liberal on what you accept, you're less likely to break downstream components. Okay. There's also a another set of laws called Lemon laws, which and Beladi, I think, and there are also laws. So I can write them here. So Lemon slash Beladi laws, also laws that are mentioned on this kind of topics. But I will not address them, but just for your curiosity, as an example of one lemon law, it's called familiarity conservation, which pretty much means that uh, the content of a system should be maintained on a level that is familiar to everyone involved on the system. Because if you're not familiar with this system, for example, you're more likely to introduce coupling as an example because you just don't know the dynamics. Okay. And so if you are familiar with the system and you are familiar with whatever is being done, you're less likely to introduce coupling. Still, yes, there's still the possibility to do so, but you're less likely to because you are familiar with whatever you're doing. Okay. But this is just one of Lemon's law. There's much more that you can go about and learn from. Okay. Yeah, that's what I wanted to share about coupling. Some of my thoughts about it. And yeah, just let me know what you think on the comments. And thank you so much for watching. And I'll see you in the next one. Bye.